I'm being recorded.
So this, I need to write it like this. Holy crap, hold on. Now, let me ask you this question that relates to a few other problems. Can I take that 1/2 and bring it down here? So I'll answer that for you. I see somebody answering me. No, you cannot. So let me ask this a different way. Why can I not take that 1/2 power and put it down here?
Is it because the 1/2 is only for the root y over 1 minus y,
Yeah.
not the entire
You can
thing?
only, I love it. You can only take a power down if it's affecting the entire thing that's inside the logarithm. Because when you put it back up, it will affect the whole thing. And then you've got a new problem. And I was like, wait a minute, how'd that magic happen? So you unfortunately can't do that. But the very first thing you can do is this is y times shit, right? Or y times stuff if you're easily offended. So how can I rewrite a log of something times something else? So I don't know how far you got with this problem.
Yeah, the natural log of y plus the natural log of 1, or plus 1/2 natural log of whatever's left over.
Okay, you got one more step ahead. So let me just do, so now you could take that 1/2 down.
Yeah, and so I was saying, can you break it up more?
Yes, because you have a natural log, you have a log of a quotient. And you did the log of a product, it's a sum of the log. So yeah, you could do a couple more steps after this, yes.
So would it be a plus 1/2 natural log y minus a 1/2 natural log 1 minus y? Or you wouldn't take the 1/2 to both?
It's got to go to both because right now it's on both, right?
Okay.
Yeah, and when it goes out here, it'll be in front of this. So if you break this up, it's going to have to be in parentheses because it was affecting the whole thing to begin with.
Okay, I understand.
Sweet, sweet. Something else you could do to really show you why it's got to be on both is, couldn't I distribute the 1/2? Get in there. Couldn't I do that? If you can see what I'm writing horribly, right? Isn't that the same thing? You don't have to, don't get me wrong, but if you did, you can see why a 1/2 has got to be with this piece and a 1/2 has got to be with this piece eventually. Did I go too far? What you said is fine, in case I lost you on something, or you just decided to stop talking. It's okay. I'll get it. How's everybody else? Anybody else? Questions? I am in section 6.4 right now, grading homework. So as you turn it in, I'm trying to capture it. I always try to grade the homework that's related to the next quiz coming up as soon as I can, but it depends on when you get it turned in. Let me see. Let me stop sharing. Go away. Okay. All right. Anybody else? Any other questions on homework? Anything we've done? Anything? No? Everybody's good? I love it. If only everybody were here. This is what I got to figure out. Everybody got the email from me being an asshole about, I'm going to drop you if you don't freaking come, right? Everybody got that one? I said it kind of differently in the email, but that was the message I was trying to get across. Okay. Because we still do have 32 people in here, so I'm only missing 13 people. Lucky 13? Okay. So let's see. And also, before I forget, 2 things. Let me show you a couple of nifty things. I added a couple of things to Canvas. One thing I added in is a practice quiz for the quiz tomorrow. Where'd you go? Unit 6, practice quiz 6. It's a little bit long, but all kinds of nice practice. And look at that. Yeah, baby. So I'm not saying the actual quiz will be this long, but this is good practice. I love it. And to make these practice quizzes, I'm taking what used to be practice tests back in the before days when it did tests. and just breaking them up into quizzes. So these are actual practice questions I did for tests back in the day. So hopefully I'll have time, as I say that I have to laugh, to make us a video of solutions, but I don't know, we'll see. I mean, if you look at that and you have questions and you haven't posted a solutions video, feel free to ask stuff. Okay, what's the other thing? I also included section 6.8, which is not on the updated homework sheet, but I was talking to somebody else and I decided to go ahead and make it extra credit if you want to do that. And the way my extra credit homework sections work is this will add on to your homework grade. So if you do all the homework and get it all right, and you do this extra credit section, you have above 100 homework average, right? Or if you didn't do a section, but you do this, it'll fill in that section you didn't do. That's how the extra credit homework kind of works. So, okay, so you can do it. If you don't want to do it, you don't have to do it. I love it. That's why there's no due date on that bad boy. You can turn it in at any time until the final. That's perfect. And then there's chapter 7 stuff just waiting. All right. Just to remind you guys, I did upload the next volume in the homework sheet, right? So winter is coming. Maybe I'll finish this someday. So our next quiz, obviously, is the 8th. It's Thursday. That's right. What was I thinking I had until tomorrow? I got more time. I might be able to make that video. I'm hopeful. Okay. Enough of all that. So let me see.
You scared me for a second, honestly, when you said it was tomorrow.
I'm sorry. It's been a long day and I'm really tired, and this will be a very interesting lesson. And somehow I thought today was Wednesday. I think that was the optimistic part of my brain. Anything else about homework questions or general questions? All right. I don't see anything. So we're going to get right back into where we left off. Let me see. Pull up the book. Get out of there. So we finished section 7.1. So what I want to do real quick is to remind you guys about something I showed you last time. Here's section 7.1. If you go all the way down, here's something else too. To be really honest, yes, I know I picked this book. I know I did. But I didn't even realize they had these links go to videos. I realized they go to videos and I haven't had a chance to even look at them yet. So I have no idea about the quality of these things, but they are there if you want to take a look. Let me see. So that was that I wanted to show you. Yeah, I'm not going to go through the whole homework and look at it so you guys can get into that. So we are getting into section 7.2 now. I believe we finished 7.1. Yes, I like it. Yeah, okay, I like it. So, all right. So I'm gonna stop sharing. So, I mean, you can see what we're gonna do. Very interesting. So here's the big deal about trig functions. So here's something I want to go over something. You guys remind me about what I'm able to do with the right triangle. So there are certain things you already know, certain things you're about to learn. So I don't think I still have that ability, do I? Did it come back? It did come back. Sorry. You're just gonna have to deal with me. Okay. So obviously, this should not be a huge problem. If I have, this is 2 and this is 5, not to scale. Let's make that 3. Can you figure out what this side must be?
A squared plus B squared equals C squared.
I love it. So we got good old Pythagorean theorem. right? It was discovered by his followers, but he took all the credit. So the most important side is the side we call C because it's the only side that the other two combine to make. So obviously this has got to be the one across from the largest angle. That's the good old hippopotamus, right? Sorry, hypotenuse. So that I'll call C. Which is A and which is B, I don't give a shit. It's summing, who cares? So I've got my 2 squared and my 3 squared. So I get C is square root of 13. All right, no big deal. That's old shit, right? We all know that. We hopefully all know that. And have you guys ever seen not really a proof of this, but a kind of a nifty visualization of what's going on? So that's good old Pythagorean theorem. So let me draw, I'm just going to erase this. Go. So let me make a general right triangle. A, B, C. If I draw a square off the edge of the triangle like this. So this will be A by A, so its area will be A squared. If I draw a square here, this will be B by B, so its area is B squared. If I draw a square here, I don't think I have enough room at all. This will be C by C, this area is C squared. There's actually a really cool video of this dude that made this. These are like containers hanging off of this thing, and it's got water inside. So if he rotates it, the water fills this up, and if he rotates it, the water fills both of these up. So this area plus this area equals this area. This is kind of a cool visualization because it's all about the squares, and in this picture is all about the freaking squares. It's kind of nice. Okay. There's like hundreds of proofs of the Pythagorean theorem. One of our presidents actually enjoyed collecting proofs of the Pythagorean theorem. It was one of the Roosevelts. I always forget which one. I think it was. Don't press me on history. I don't know. All right. So that's old news. What we are working towards is what if what really happens in real life? What if I knew there's a tree here, right? Here's a tree, whatever. There's a tree here. Just deal with it. That's a tree, believe it or not. It's a pole, whatever. And I know how far away from the tree I am. And then I've got this, what's it called? Not a sextant. Is that the thing on the boat? So it can measure the angle that I'm looking up at. So I put in my eye, look at the thing, and it can measure the angle. So I know what this angle is. And I'm curious how tall that tree is. Is there a way to figure that out? Yes. If I knew, what would I have to know for every angle to be able to figure this out? That's a very, very vague question, but what kind of makes sense here? There's got to be a relationship. If this was actually taller and further away, it would be the same angle, wouldn't it? It would be the same angle. But the ratio of this side to this side seems to remain the same. Let me say this again. So if I have a tiny triangle with a little angle, X and Y, and let's say it actually, I go, no, I'm sorry, I meant same angle, it's just a bigger triangle. Same angle, but now that's X and Y. It looks like the ratio of those two should stay the same. In fact, we know they do. We know they do. Let me stop for a minute. How do we know they do stay the same? Well, because if the little triangle was, if this is 3 and this is 4, does anyone already know what that side length is without doing any work? 3, 4, what? Does anyone know that kind of triangle? 3, 4?
5.
5. I love it. So if you do 3 squared, 9, plus 4 squared, 16, that's 25, which is 5 squared, so that's 5. If that is 12 and that is 9, what must this be now? So here it is, and then I blew it up. So
15.
now that's 12. Yeah, it's got to be 15. So the ratio 3 to 4, does it stay the same here?
Yes.
Ratio, yeah, it's almost like a silly question. Of course it does, Jeff, because we multiplied all the sides by the same number. So of course the ratios of the sides stay the same. Let me stop for a minute. So if I blow this thing up or shrink it down, the ratios of all the sides, right? 5 to 4, 15 to 12, they're equal. The ratios between all the sides stay the same when you reduce them, but they're the same number. Is everybody cool with that piece? It's almost kind of like, well, duh, Jeff. The only way I can change the ratio of the sides is to change the angle. Is that okay? You guys see that? If I change the angle, doesn't that change? It's not going to be 3 to 4 anymore. If I make that angle a little bigger than it currently is, so I make it like this, that side looks longer than that side now because the mouth is opened up more, right? If your mouth opens up more, you can put a bigger stick in it. I'm always thinking about Return of the Jedi when he puts the stick in the Rancor's mouth. But anyway, yes, I'm such a geek. It's amazing. All right. So watch. What kind of, does that make some sense? I really want to know if it doesn't, because this is another thing. This is why I teach courses so often based on something I found out later that I wish my teacher would have told me right when I learned the shit, right? And one thing that I really make an emphasis about is the idea of trigonometry is built on ratios of sides of triangles. That's all it is. And why does it make sense? So for example, if I said for a given angle, whatever this angle is, I could say the ratio of this side to this side will always be the same number, right? If I make it bigger, same angle, that ratio will still be the same number. It'll still be 0.75, right? 3 divided by 4. So for every angle, I can define, so for example, this is my y side to x side function. I really want you guys to stay with me. And then I could define a different function that would be like, let me put a little h for hypotenuse, an x to h function, what else, a y to h function, and then all the other ways around. All right, let me stop for a minute. So what I'm really trying to get across to you is, for a given angle, no matter how big or small the sides are, their ratios will remain a constant. Any ratio I make. So I could have a function that is devoted to the y to x ratio for any angle. So this is a different angle. Its y to x ratio would be different. So the function would have a different output for this angle than it would for this angle. Let me make this a different, let's use a different letter. Beta. Yeah, buddy. All right, maybe. So let me bring this into the realm of more formalized instead of just kind of vague. So here we go. Let me give us some names to work with. So if I have a triangle, let me call this, I'm going to call this angle A, angle B, yeah, angle C, which is the hypotenuse. I'm going to call this side Y, side X. I'm going to call this R, and you'll see why not too long from now. So that is the hypotenuse. It's supposed to be an R. All right. Really want you guys to get this. I'm going to create a function that represents what the y to x ratio, or let's start with some of the more basic ones. The x to r ratio is. So this function, when I put an angle into it, it will give me the ratio of x to r. So for example, for a 3, 4, 5 triangle, this function would give me 4/5. And the symbol we use for this function is cosine. This is actually fully written out. That's the symbol we use. And the full word, sort of like log is shorthand for logarithm. Cos is shorthand for cosine. All right. So all this function does is for a given angle, and I really want you guys to get this. If somebody just gives me an angle, A, and then I say it's the ratio of the x side to the r side, well then, how far could these go if I've just given the A? They can go forever. They could go just to right here. And like we just figured out, it doesn't matter. The ratio of this side to this side will always reduce to be the same damn thing, no matter how big or small I make that triangle coming off of that angle. Let me stop. That is why if I say cosine of 30 degrees, there will be one answer. It will represent the reduced form of the sides of a triangle with 30 degrees right here. All right, let me stop for a minute. Do you guys kind of get what I'm saying? You don't have to 100% get what I'm saying. Maybe some of you guys have taken trig before. Hopefully you see where I'm going with this. All right, maybe. So let's introduce one more. Let's do the y side. So the function that gives me the ratio, let me get rid of that for right now. That gives me the ratio of y to r is sine. Okay. So I want to do a couple of specific triangles to get a couple of specific answers to this. So everybody got what they want from this craziness up here? All right. Let me bring back my, where'd you go? There you are. I'm going to erase this. It's nice to do it. All right. So now watch this. I'm going to draw this a little bit strange, but oh well, too bad. Oh, that's really strange now. I want an equilateral triangle. Dude, it doesn't have to be perfect. Just deal with it. Okay, that's not bad. That's okay. I'll deal with it. Okay. Could use the nose draw for this one. What's it mean, equilateral triangle? What are all the angles in an equilateral triangle?
They're all equal?
They're all equal because lateral is sides, equilateral means equal sides. If all the side lengths are the same, let me make them 1. That means that all the angles are the same, 60 degrees. So if I cut this right down the middle, right? I take my laser and I just chop this triangle in half. Poor little dude. And I throw this bottom part out. So let me redraw it. I throw out this guy. Yeah, you're dead. Get out. You kind of redraw this crap in half. Oh. How long is this side now? Right, so I just took this top half and put it here, and I dropped this one out. How tall is this?
1/2.
1/2. What this is still 1, right? We don't know what this is, right? What's this angle right there?
30.
30. I love it. So what? And of course, this angle is still
60.
60. I love it. Now, notice I am doing this with degrees, just because I don't want the radians that we're not quite used to yet anyway getting in the way. You know radians are going to come back, right? But right now, I just want to work with something we're more familiar with. So what does cosine need? What does cosine tell me? So cosine of 30 degrees would be the ratio of what side to what side?
Adjacent over hypotenuse.
So you're using words that are
X to
fine.
R. So
Yes. And by the way, if anybody knows, all right, I don't know. I don't care if you're going to hate me for this. If anybody knows Sohcahtoa, I wish that thing did not exist. It is not helpful in the long run. I will discuss it a little bit because the book talks about kind of adjacent hypotenuse kind of crap. But cosine likes X. Sine likes Y. So as long as the angle is right here, if the angle is in the base, cosine is based on the X side, sine is based on the Y side. That is a much more useful way to look at those for the long run. People that know Sohcahtoa really well kind of die in my calculus classes because they're not looking at it in the most useful way. So in general, cosine of an angle tells me X to R. What is R in this triangle?
R is 1.
R is 1, so I know that's a 1. And how do I figure out what X is?
Multiply?
No.
No. No.
What relates all these? What we were doing earlier. Old Greek, dude.
You could use Pythagorean Theorem.
Totally, yeah. So what would that say? That would say 1/2 squared plus
X squared
say again, sorry.
plus X squared equals 1 squared.
Equals 1 squared, 11. So that's 1/4. If I subtract a 1/4 from 1, I get 3/4. And then if I take the square root, we're going to pick the positive one because this is right now, this is physically a length, but the negative is going to come into play later. So we're going to pick the positive root. So I'm going to get square root of 3/2. Is that, you guys see that? So then what's the cosine of 30? It is X over R. So it is square root of 3/2/1. So the cosine of 30 for every damn thing in the universe is √3/2. That is, I really want you guys to understand that. Cosine of 30 is √3/2. Doesn't matter. Doesn't matter. Nothing else matters. That is it. Because if I had a different triangle, if I had a 30, 60, 90, and I made a different size triangle, it would be the same ratios. It would reduce to be this anyway. All right. What's let me get rid of this. Go away. What's sine of 30 degrees? What's sine? I'm sorry, go ahead.
1/2. Because it's 1/2 over 1.
Yeah, so sine in general tells me y to r. So sine will be 1/2 to 1, so it's just 1/2. I like it. I like it. Kick ass. Kick ass. So let me introduce a third trig function. This is the one that kind of seems like we should stop here. Let me see if it makes sense to you. So Sine always tells me the ratio of y to the hypotenuse. Cosine tells me the ratio of x to the hypotenuse. This guy, tangent, so this is the word tangent. That function always tells me for any given angle, it tells me the ratio of y to x. All right. So let me show you right now. Well, first off, let's figure out what tangent of 30 is. What would tangent of 30 be? There's two ways to kind of get this, but it's going to be the ratio of y to x, right?
One half divided by the square root of 3/2.
And what happens to the halves?
They cancel.
Cancel. So I get 1 over rad 3. Now, a skill that you need to have is how to rationalize that. That's getting lost down the poor little dude.
Multiply the top and bottom by rad 3.
Yes. So that would become rad 3 over 3. Become a 3. Multiply top and bottom by rad 3 to rationalize the denominator. I like it. And that just means exactly what it says. It's irrational now. Hey, now it's rational. I rationalized the denominator. This is not a psychological thing, by the way. It's just making it a rational number. It's not making it okay in your head. Okay. So let's do a couple of things. Let's do, which order do I want to do this? Yeah, let's do this. Let's do a concrete problem real quick. Two different types of concrete problems. First kind of concrete, sure, Jeff, that you'll see is something like this. What you got, Jeff? So let's make this 5, 12, 13. You can double check that. I can't just make all these up, right? So there's a 3, 4, 5 triangle. There's a 5, 12, 13 right triangle. There's only certain triangles that are whole number size. Okay. So can somebody tell me what is the sine of A?
Five thirteenths.
I love it. Well, yeah, good. I like it. What was I looking at? I was looking at somewhere. Looking at my computer screen. Yeah, it's the ratio of y to hypotenuse. So 5/13. I like it. So, I mean, this kind of problem you should eat up. Now, let me show you one kind of problem where Sohcahtoa sort of helps. And I really don't even want to show you Sohcahtoa, to be honest. If I ask you about B, let me see if somebody was paying attention earlier. Why does this not quite relate exactly? Because where's angle B? Is it where it's supposed to be? This works perfectly because the angle is in the base. That's why I can look directly at this. That's why Y is in the right place and R is in the right place. Angle B is up here, right? Stay with me, stay with me. So I need to do this in my head. I don't know, can you guys see me? I need to do this. Or you can redraw it so that it's in the base. So that would be down here now, that would be there. This is 13 still, this is 5, and this is 12. So now what's cosine of B? Cosine tells you x to r, so what's cosine of B? What's the x piece in this triangle?
Wouldn't it be 5/13 also?
Yes, I love it. Exactly. Yeah. And we're going to get into why it makes sense that these two are the same. And really it's because if I look at A, then 12 is the base. If I look at B, now 5 is the base. So if trig functions are equal to ratios of sides given an angle, well, if I'm given A, it creates this triangle. If I'm given B, it creates this triangle. So I have to kind of rotate it so that's in the base. All right. That's the one thing you've got to be careful about if you're using those definitions for sine, cosine, and tangent. If you know, all right. So I might as well just tell you. I really, really dislike this because it will hurt you later. But if you look in the book, they will describe sine, and this is the so part of Sohcahtoa. Sine is opposite over hypotenuse. So sine, let's look at A. Opposite over hypotenuse, 5/13. But this is so important. You need to really get it in your head that sine goes like y. Sine is related to the y piece. Cosine is related to the x piece, but it's got to be in relation to the angle. So cosine of an angle is, and this is the ka, so ka is adjacent over hypotenuse. So what's the angle adjacent, what's the side adjacent to B that's not the hypotenuse? It's 5, right? So it'll be adjacent side divided by hypotenuse. All right, so if you look at the book, that's what these, and then of course the end is tangent, which will be opposite over adjacent. And then there's all kinds of stupid jokes about that sounds like a camp. I go to Camp Sohcahtoa for the summer, whatever. In case you've seen that before, I will justify its existence. I will tell you that that will not help you in the long run. And then I'll let you decide how you want to look at these. All right, maybe.
I do have one question about the tangents. So
Yes.
you said that sine is related to y and cosine is related to x. How should we think that tangent is related?
All right, so here we go. Tangent is really, really, really neat. Y over x. Where else in algebra have we seen something about y's over x's? Anywhere in algebra we talked about y's over x's.
Slopes.
Slope. So tangent is actually the slope of the line. It's kind of neat. But so tangent is going to be the y piece over the x piece. And I can look at it like this. Tangent, let's see if you guys agree, is sine divided by cosine. That's another definition of tangent. What do you get when you do sine divided by cosine? The r's cancel, you get y over x. So what I really want you to think about, I'm not saying this is going to help you memorize stuff, but as we learn more complicated trigonometric things, remember that each of these is just the ratio of sides of triangles. That is all they are. How can we use them? In crazy ways, so many ways, but they always boil back down to sides of ratios of triangles. Ratios of sides of triangles. There's the right way to say those. Okay. So let's do the second kind of problem I wanted to do. Did I erase those? I did. Yeah, damn it. Let's see who is paying attention. Who remembers what sine of 30, or can you look it back up? Sine of 30, what was that? We already
1/2.
proved. Yeah. What about cosine of 30?
The square root of 3 over 2.
Kick ass. I like it. And of course, tangent, we've got
The square root of 3 over 3.
love it. Okay, now watch. The immediate usefulness of these is that problem I described earlier. So if I had a right triangle, so again, let's go back to our tree. And I know, and I walk off this, and I know that this is 22 feet. And I know that this angle, so I got the little weird thing, put it up to my eye, look to the top of the tree, and then I can see what the angle is. And I know that this angle is what makes sense, Jeff. I don't know. Let's just make something up. Oh, it's got to be 30. I'm getting a little ahead of myself. We don't know how to do anything except 30 right now. That's all we know. Can I figure out how tall that tree is?
Yes.
Totally. Because I have, which function would I use to figure out how tall that tree is?
Tangent.
Exactly. How did you figure that out? Because I have one side that I know, and that's the x side. I have one side that I want to know, and that's the y side. And then I have one side I don't give the first shit about. So I'm not going to use sine or cosine. It's got a side I don't give a shit about. I don't know it, and I don't want to know it, right? Maybe. So if I just knew what this divided by this is, I could solve for this. Does that make sense? If I knew that y divided by x was 7, couldn't I put 22 in here, multiply, and then I know what the hell y is, right? Maybe, yes. But I do know what y divided by x is, don't I? Y divided by x is tangent of 30, right? Is that? That's what tangent 30 is. And what is tangent 30? What's tangent 30?
Square root of 3 over 3.
I love it. So now let's throw in what else we know. We know x is 22. So I get y over 22 equals rad 3 over 3. And now I can solve for y, which is exactly what surveyors do and other people when they do this kind of thing. I don't want to climb the damn tree, but I can walk off a certain distance, look back up at it, use trigonometry. Now I know how tall the tree is. And of course, you will do this. And since we're talking about a freaking tree, we're going to make that into a decimal so that people don't look at us weird. How tall is that tree? About 7 rad 3. What? So, whatever the hell that is. I'm not going to pretend like I know. Let's see. I'm going to do it. Come on, Jeff, you can do it. Twice. 7, 1.
12.7018.
I was almost there. 12 point who?
7018 if you round up.
7, 1, sure.
Yeah, there you go.
How many units?
Feet.
Oh. Just go with me. I know I said how many units. 1, that would have been a great answer, but you know what I meant. Okay. So I like showing you that's the immediate usefulness of this. We had no idea. If I knew this angle and knew this, it's like, okay, that's great that I know that shit. I need to know this side to do Pythagorean Theorem. Well, now we can screw Pythagorean Theorem. Thanks, Pythagoras. We don't need your shit. We can do this now. All right, so it's obviously pretty important to know a few of these. And eventually I'm going to let you use your calculator, obviously, because we're not going to learn sine of 11.297 degrees. You're not going to have to memorize this. You are going to have to memorize some main angles. Obviously 30. You must memorize this. And I will show you a very cool and easy way to memorize these. At least I think they are cool. Okay, so everybody got this here? Okay. Maybe. Let me see if you guys get
Is
this
there a
idea.
song to memorize them?
A song?
Yes.
There could be. I don't have a song for them, but
Okay.
anything made into a song. There's probably some silly video out there about a song. I don't really do a lot of songs.
You sing almost every day before class. What are you talking about?
But what I mean is to memorize mathematical ideas. I am not a fan of a lot of mnemonic devices. I'm not a fan of not too many of them. And you can take that as you want to. But I personally think it takes us away from the idea. I want us closer to the idea so it continues to make sense. Instead of, anyway, that's all beside the point. So what I want to do is remember where these came from. They came from the 30, 60, 90 triangle, right? So I don't know if you guys noticed this earlier. If I draw it like this, now 60 is in the base. So earlier we had it drawn with 30 in the base, right? And we had, this was 1/2, and this was rad 3 over 2, and this is 1. So notice, I really want you guys to get this. This to me makes things make even more sense. So this is why we saw that relationship earlier between that triangle where I said cosine A and sine B, and they came out to be the same ratios just a minute ago. So if I do this, now rad 3 over 2 is here, 1/2 is here, and this is still 1. Is that cool? But now can somebody tell me what is sine of 60? Now that I've got it in the base, what's sine of 60? Should do this in different color. What's sine of 60 degrees?
Radical 3 over 2.
Yeah, rad 3 over 2, which is equal to cosine of 30. Oh, interesting. What is cosine of 60?
One half.
Yeah, likes the x side, so 1/2. And what's tangent of 60?
Would it be rad 3?
Yeah, rad 3. The over 2's would cancel. So remember, tangent is y divided by x. The over 2's would cancel. And that is the reciprocal of this. Which kind of make, if these switch places and tangent's y over x, then this will now be rad 3 over 1. That'll be what that is. Maybe. Okay. And why that makes sense, let me see if I can explain what I mean. If I let this thing grow to 60 degrees, I should have given myself some more room. If I let that grow to 60 degrees, but I want to make this stay 1, okay, that's really weird. I should probably wait until we do unit circle, but if I want this to stay 1 and I want to make this grow, doesn't this have to open? I really want you guys to get this because this is kind of cool. If I want to make that a bigger angle, don't I have to open this? But if this stays 1, can it reach over as far? What I mean is it's not going to go all the way over here. It's got to still be 1. It's going to be back here a bit. So isn't the y side going to get bigger, but the x side is going to get smaller, right? Until I get to here. If I just keep going, keep making it bigger, keep making it's going to get to here. And they're going to switch. So if these two, if these two add to 90, then this kind of thing is going to happen. If sine of 30 is 1/2, then cosine of 60 is 1/2. So if sine of, get in there. If sine of theta is 1, you could do it, Jeff. Yeah, it doesn't matter. If sine of theta is 1/7, then what is cosine of 90 minus theta? 1/7. That's the kind of generalization I can make here. All right.
So would the sine of 45 equal the cosine of 45?
That is the one place they agree. I love it. And what I'm going to do, since this is sort of screaming for me to do this anyway, I'm going to jump a little ahead. I'm going to talk about what's known as the unit circle real quick. And I think it's in the next section, but too bad. This is a really good place to talk about it because we're sort of there already. I'm going to take all this away. Is everybody all right? All right. Maybe I should do that first. Let me do that first. Thank you for that, Jason. Let's see, what's a good way to do this? Yeah, so if I have a 45, 45, 90, then I can investigate sine, cosine of 45, because that's the other major angle. So we got 30, 45, 60. And then we're going to talk about 0 and 90. Those are extreme situations. If this side is 1, can you figure out what these two sides must be? Don't go off the scale on my picture. My picture is shit, as usual. So I'm going to try to make it a little bit better. These two sides have to be how related?
They have to be equal?
Yeah, because their mouths open the same amount, so you can fit the same size stick in each one. Right? I know it's a very strange way to look at it. I don't care. Now, can somebody figure out exactly how big they should be? If this side is x, this side is also x. Set up the equation, solve it, I'll wait.
It's rad 2 over 2.
Yeah, because you get x squared plus x squared equals 1 squared. So you get 2x squared equals 1 squared. Divide by 2, take the square root. So you get 1 over rad 2. And if you rationalize it, you get rad 2 over 2. And then you can see why cosine and sine are equal, because 45-degree angle is where they both have the same sides, both of these sides. So what is cosine of 45 degrees? What's cosine tell you always? It tells you the ratio of x to r. So what's cosine of 45?
Rad 2 over 2.
Yeah, rad 2 over 2. What's sine of 45?
Rad 2 over 2.
Craziness. And what's tangent of 45? This kicks ass.
Isn't it just 2?
Nope. Careful.
1?
1, because it's going to be this divided by this, which is 1 divided by itself. Like. All right, so I think, so we've got a complete picture here now for 30, 45, 60. You must memorize those. If you give me a minute, I'm going to show you a really kick-ass way to sort of put everything we've talked about into a context that will help you memorize these things. All right. Oh shit, should have asked you if that was okay. Hopefully everybody got that. So if I have what is known as, okay, here we go. That's not bad. It's like Stewie's head, but it's too bad. Okay, math boy. This is called a unit circle because its radius is 1. That's crazy. So it's radius 1 on the y. Draw my ones differently. Too bad. So for example, let me put a 45 in here real quick. So this would be, yeah, sure. I'll do this in purple. 45-degree angle. And see how I drop that down. So there's a triangle that lives inside this unit circle. Right? And I know what are the coordinates of this point here. That's such a weird question, and I love it. Won't the x coordinate be the cosine of 45? Because what's this? How long is this?
1.
1, because that's the radius. It's just turning around. No big deal. So it's 1. So that means that this will equal the cosine of 45. And what's the cosine of 45?
Rad 2 over 2.
Rad 2 over 2. And of course, the y piece, how long is this, will be the sine of 45. So that's also rad 2 over 2. And that makes sense because it's exactly 45. It's exactly equidistant in all directions. Okay. So now watch. This is what I was trying to say a minute ago. If I let this sucker move until it's got an angle of 30 here, look what happened to the y side. The y side got much smaller, and the x side got comparatively larger, which means the sine of this angle, let me make sure that's a little bit bigger. Why did I make everything so tiny? The sine of this must be smaller because the sine likes y. I don't know how I'm trying to make a y with my hands. The cosine must be bigger because the cosine likes x. Who remembers what the sine of 30 is?
One half.
1/2. And the cosine is going to be the other piece, rad 3 over 2. And then, real quick, if I do 60 degrees, that's the one we just did a minute ago. So if I make a 60-degree angle here, that's just going to turn these around, isn't it? That's what we found out earlier. Because now what's going to happen is that's going to be this long, and this is going to be that long, if my scale was better. So now visually it makes sense why whatever is true. I'm sorry, did I motion to the wrong triangle? So this is this, and this is this. Let me stop. Did that make sense? If you're reading a transcript of this later, it's not going to make shit sense. This is this, but this triangle, this red triangle, isn't it the same as this blue triangle? It's the same freaking triangle, just rotated and turned around. So that's why the sine of 30 is equal to the sine of 60. I'm sorry, cosine is 60, and the cosine of 30 is equal to the sine of 60. That length is that length. That length is that length. Become a 3. Okay. Stay with me now. I'm not there yet. If you're like, this is not impressive, Jeff, this is not going to help me remember shit, I agree with you. Just give me a minute. This is an extreme one. What if I'm at, what angle is this? What angle is this?
0.
0, kick ass. So if I'm at 0 degrees, remember, this is what's going to help you. The cosine is the x piece, and the sine is related to the y piece. So at 0 degrees, what is there none of? It doesn't have what, x or y. It doesn't have any what piece. It's all what and no what.
It's all x, no y.
All x, all day. So, and you already know what point that is. It's freaking 1, 0, isn't it? So the cosine of 0, become just a 0, become a 0, there we go, is 1. That is where the cosine is biggest, because that's where it's all just x. It's not sharing any of that radius with the y direction. So the minute I lift up, oh shit, he lost a little bit because he had to share some of it with the y. Oh shit, he lost even more because he had to share more. Oh shit. Maybe. That's my aw shit approach to teaching. All right, now here's where the cool shit comes in. So what do you think this is? That's 90 degrees. So what do you think the, I'm sorry, real quick, what's the sign of 0? It's all x, no y. So what's the sign of 0 degrees?
0.
Because there's no y piece to 0 degrees. So there's 0 y piece. So what do you think this is? What's the cosine of 90? Become a 90. Cosine likes x, and this is nothing but
0.
nothing but y. So this will be 0, and sine of 90 will be 1. Like, now watch. Last thing, I think. Sure, last thing for today. Here's the neat part. Ready? Let's follow. It's pretty cool with the fact that this second piece is the sine, right? Because sine likes y. So watch this. Can I write 0 as square root of 0 over 2 if I was really feeling weird? Isn't that what 0 is? Another way to write 0? Yes? Maybe? Yes, it is. And then if I do a tick, doesn't it become square root of 1 over 2? Stay with me now. Isn't that what happened? And isn't that 0? Now take another tick. So what's it going to become now? Square root of 2 over 2. Is that what it is? Holy shit. If it goes another tick, what does it become now? Square root of 3 over 2? I don't know. Do you guys understand? This is such a useful thing. I really want you to understand because you have to memorize all this shit. I just want you to be able to, and the beautiful thing about this method of memorizing this is it reinforces that as the sine piece gets larger, the cosine piece gets smaller. So the cosine piece does the exact opposite. And of course, what's the next thing? Well, following this pattern, what would the next thing be? This pattern, what would the next thing be for this pattern?
1.
For this
Square
pattern.
root of 4 over 2, right?
Which is 2 over 2, which is 1. So that pattern beautifully holds. So what does sine do? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. I don't know. If that doesn't really help you, you don't have to use that. I just got really excited way back in the day when I figured out this little pattern. I think I saw it in a book somewhere finally. Yeah, maybe. Where things get a little weird is what happens when I get into these other quadrants. Because look here, isn't x going to be negative back here? So for example, I promise that this will be the last thing. I think I've said that 3 times. Remember when I talked about reference angles? So if I'm 30 degrees away from that side, isn't that the same triangle as this? Aren't these the same triangle? Yes? Are you guys with me? Okay. That's the same exact triangle. The only difference is the x side is going to be negative now. So at 30 degrees, instead of being rad 3 over 2, 1/2, it's going to be negative rad 3 over 2, 1/2. Can somebody tell me what angle this really is? What angle is that really, if I go this way? What angle does that really represent?
It's 150.
150, I love it, because of course, become a 0 and then a degree. Because that's 180, and that's 30 back from it. I love it. So what is the cosine of 150 degrees? It's equal to negative rad 3 over 2. Because the reference angle tells me, so that's why you only have to memorize stuff in the first quadrant. And then when you're in the second quadrant, all the x-related shit becomes negative. If you're in the third quadrant, the x and y related shift become negative. And when you're in the fourth quadrant, the y shift becomes negative and the x shift stays positive. You just have to memorize these and then they'll repeat. Because if I come here and I start going back down, they start shrinking in the exact same pattern, except the x's are negative. That's it. So, am I really gonna? I'm gonna post a handout up on Canvas that has a completed unit circle on it. It's also got extra shit on it, so I might not do it too soon. But I will post one that's got all this kind of completed, so it can be a nice reference. It's got some other stuff on it too that I want to talk about before I post it up there. But I will eventually have that. All right, and I think that is a lot that we have done, or that, we all have made it. If you want to hang out, let me know. Otherwise, class is officially over. Let me know if you have any questions anytime. I have all this math in me and it just comes out. It's crazy. Everybody good? You guys all right? All right, I'm out of here. See you guys.